In this video, we're going to apply the cross product to a problem in 3 parts. So we have an example here. We're going to start with this triangular plane identified by these 2 vectors, PQ. It's a different color there. We got PQ and PR. So PQ and PR create this triangular plane. The first thing we're going to do is to find a vector perpendicular to the triangular plane. So the vector that would be perpendicular, or a vector that would be perpendicular, is going to be the cross product of these 2 vectors. So we need to know what PR and PQ are. The vector PQ, it's going to be the difference Q minus P for each of these components. So we end up with 2 minus 1, which is 1, 1 minus negative 1, 2, and negative 1 minus 0 is negative 1, or rather I plus 2j minus k. And PR, that vector would be negative 1 minus 1, or negative 2, 1 minus negative 1, positive 2, and 2 minus 0, 2. So I have negative 2i plus 2j plus 2k. So in order for us to find a vector perpendicular to this triangular plane, we're going to need to find the cross product. That's what the definition of the cross product is. So PQ cross PR will be I, J, K. I'll list 1, 2, negative 1, and negative 2, positive 2, positive 2. So this is the determinant of this vector of a 3 by 3 matrix. And this is going to equal I times the determinant of the 2 by 2 matrix, negative 2, 1, 2, 2, minus, it's always a minus, second, j, times the determinant of the matrix, 1, negative 2, negative 1, and 2, and plus k times the determinant of the matrix, 1, 2, negative 2, and 2. So that gives us I, negative 2 times 2 is 4 minus negative 2, 2 times negative 1 would give us negative 2, minus j, 1 times 2 is 2, minus negative 2 times negative 1 is positive 2, plus k, 1 times 2 is 2, and need a minus there. We have negative 2 times 2 is negative 4. So that simplifies to positive 6i minus 0j plus 6k, or rather 6i plus 6k. This represents a vector perpendicular to the plane formed by the vectors PQ and PR. Part B of our problem asks us to find the area of the triangular plane. Well, for part B, in order to find the area, that's just the magnitude of PQ cross PR. Now, that vector is going to be the magnitude of the parallelogram, right? So if we think about this, creating a parallelogram, what we know is that the magnitude of that cross product vector gives us the area of the parallelogram. When we're dealing with vectors, we use this parallelogram law to help us find sums and differences. So working through this, we're going to find a magnitude. We need to find the magnitude of this vector, 6i plus 6k. That's the sum of the squares of the components. We take a square root, so that's 6 squared plus 6 squared, or we get 36 plus 36, 72, and the square root of 72 simplifies to 6 root 2. So that represents the area of the parallelogram. The problem asked us to find the area of the triangular plane. Well, that triangular plane is going to be half of this. So the area of the plane, so the area of triangle PQR, would be half of that, or 3 root 2. Lastly, part C asks us to find a unit vector perpendicular to the triangular plane. So what we have here with 6i plus 6k, that is a vector which is perpendicular to the plane. So a unit vector is found by taking a vector, 6i plus 6k, and dividing it by its magnitude. Now, we have the area here, 3 root 2, but the magnitude of that vector was 6 root 2. So simplifying this, we'd get 1 over root 2i plus 1 over root 2k. And that represents a unit vector. If we have 6 of those unit vectors, that's going to represent our perpendicular vector that we found. So I hope that helps. We have one more topic to discuss in this video, and that's going to be torque. Here we're going to talk about torque. When we turn a bolt by applying some force, some downward force in this situation, F, to a wrench that you see pictured here, we can produce the torque that causes the bolt to rotate. The torque vector points in the direction of the axis of the bolt according to the right-hand rule, so that the rotation is counterclockwise when viewed from the tip of the vector. The magnitude of the torque depends how far out on the wrench vector that the force is applied, right? So obviously the further out you are, the more torque you would get. And here we would have less torque. And then also on how much of the force is perpendicular to the wrench at the point of application. So the number we use to measure the torque's magnitude is a product of the length of this lever arm R and the scalar component of F, that perpendicular force being applied to R. So in notation, what we can say is that the magnitude of the torque vector that's going to equal the magnitude of R being the length of the lever arm, times the magnitude of the force applied perpendicularly, so we use sine theta. And that's really essentially equal to the magnitude of R cross F. So if N is a unit vector along the bolt in the direction of the torque, what we can say is that this torque vector is equal to R cross F, which is equal to the magnitude, that's not how we draw magnitude, the magnitude of R times the magnitude of F, sine theta times that normal vector, N. Remember that normal vector is a unit vector. So in practice, let's view an example. Here we have a 3-foot bar, and there's a force being applied to the bar at a 70-degree angle. So the magnitude of the torque generated by the force F at this pivot point, P, that's where we're turning, I should say, So the magnitude of that is the magnitude of the vector PQ cross with the force vector, which is the same as the magnitude of PQ times the magnitude of the force vector times sine of that angle at which we're applied, or rather the angle at which we're applying our force. So the magnitude of PQ, we've got a 3-foot bar, 3. The force we're applying is 20, and that downward component of that vector is going to be the sine of 70. So simplifying this, we can plug this right into our calculator, making sure we are in degree mode since that angle is given in degrees. And our solution is approximately 56.4 foot-pounds. All right, and in this example, the torque vector is pointing out of the page towards you. So I hope that helps you see the relationship between vectors and the cross product and torque. We have one more video we're going to do in this series, and it's called a triple scalar, or also a box product, meaning the same thing.